Just like Chapter 8 was a continuation of Chapter 7, talking about vibrational modes, Chapter 11 is a continuation of Chapter 10, where we're going to be talking more about many electron atoms. But we're going to focus a little bit in on the quantum states of those atoms, particularly on the spectroscopy that we see when we look at electronic transitions. Now, as we've mentioned in the past, rotational spectroscopy is done with microwaves. Vibrational spectroscopy is normally done with infrared waves, but we also can look at some transitions with visible waves, but they end up absorbing an amount of energy associated with infrared. Atomic spectra can be done in a number of different ways, but typically we're looking at visible or ultraviolet light. The lines in a spectrum for a particular atom occur when the electron distribution undergoes a transition with a change of energy and emits a photon that has a frequency that's associated with that change in energy. It's delta E over H. Not all transition are observed, so we're going to learn some selection rules in this regard as well. One of the things that we have to realize is that a photon has an intrinsic spin angular momentum that corresponds to S equals 1, and that angular momentum is always conserved. So not only will a transition have to change the energy by the amount of energy associated with the photon, but there will also have to be an angular momentum transition as well. And so the change in angular momentum of the electron that gets hit with the photon and absorbs the photon has to compensate for that angular momentum. So that means that what we're going to see usually is delta L's change in angular momentum quantum number of 1. Jumping from an S to a D orbital would be too much. Jumping from an S to an S orbital would not be enough of a change in angular momentum. Jumping from an S to a P, or from a P to a D, or from a D to a P would be enough, would be just the appropriate amount of angular momentum change for absorbing a photon. So as I was just saying, delta L is going to be plus or minus 1. Delta M sub L is going to be 0 or plus or minus 1. For hydrogenic atoms, what we mean when we say hydrogenic atoms or hydrogen-like atoms is atoms that have one electron. And this diagram gives us some examples of how hydrogen atom transition occurs. So notice there's no jumps from the 1s up to the 2s. There are jumps from the 1s up to the 2p, and then we can go from 2p to 3s and so on. But the amount of angular momentum change, the amount of L change, has to be plus or minus 1. Selection rules in general state that in order for a particle to interact with a photon, there must be a transition dipole caused by the interactions. That's in addition to this new selection rule. Hund's rule, we talk about singlet and triplet states. Did I just disappear? Hund's rule of maximum multiplicity tells us that unpaired electrons are far more likely to have parallel rather than anti-parallel spins. Both, however, are allowed and can make up a distribution of excited states. So, for example, with nitrogen atom, we've always drawn it as 3 up arrows in the 2p. It's possible for it to be up, down, up, or down, up, down. But it's less likely. It's not energetically favored. But we can see the evidence that they exist in spectroscopy if we do it with high enough precision. Electrons in general do not change their spin during a transition, though. So if something is spin up when it gets hit with the photon, it's going to be spin up after. and it's going to be spin up after it releases a photon. Electrons have an angular momentum associated with their spin as well as with their L designation, with their L quantum number. And those two angular momenta, the angular momentum that's associated with their orbital shape and the angular momentum associated with their spin, can couple with one another in some cases. So electrons with L greater than 0 have an angular momentum as a result of their orbit. They also have an angular momentum as a result of their spin. Spin-orbit coupling, so there's a vocabulary term for us, is a magnetic interaction between spin and orbital magnetic moments. The total angular momentum quantum number for an electron, then, we're going to call that number J, and it's going to be L plus 1/2 for parallel spin and L minus 1/2 for anti-parallel spin. And here's an example of an equation that will give us delta L for a particular transition as J and L and or S are all changing. When the angular momenta are lined parallel, they interact unfavorably and the system is at higher energy. When the angular momenta are aligned opposite or anti-parallel, they interact favorably and the system is at lower energy, just like magnets. When they align north to north, they repel. When they align north to south, they attract. A in this equation is the spin orbital coupling constant for the particular atom. So each atom is going to have its own A. It goes as, or is directly proportional to, z to the 4th. So that number gets very large very quickly as we start talking about atoms that have more than one electron. This means that in hydrogen we would see shifts of about 4/10 of a reciprocal centimeter that are caused by spin-orbit coupling. In lead, we can see thousands of reciprocal centimeters because this A becomes so large. An example of where we see this is in sodium. If you've ever looked at a parking lot lamp and it had a really yellow color to it, that's a sodium lamp. And so you're watching the visible transitions in sodium as sodium atoms are being excited and decaying their excited state. And so what we see if we separate that with a really high precision prism is that that yellow is caused by two wavelengths, both of which are caused by a transition from 3p down to 3s. And so let me move myself a little bit so that you can see the diagram a little bit better. The difference in lines that we see here is called the fine structure for the atomic spectrum. And so what you see as a line near 589 is actually two lines if we separate it out well enough. And the difference in energy between one 3p orbital and another 3p orbital has to do with how the spin and angular momentum of those two orbitals line up with one another, how they whether they are in line or out of line with one another. So the p sublevels have different energies as the electron jumps to them, depending on whether the angular momentum is in line between the electron spin and the orbit angular momentum. This is going to bring us to a point where we have to start to understand that the quantum numbers that we've used in the past, n, l, m sub l, and m sub s, are not necessarily going to work for atoms that are larger than hydrogen. We call them good quantum numbers because the operators that generate them, Hamiltonian generates n, L squared generates L, LZ generates m sub L, S squared generates m sub S. They all commute with one another. Because they all commute, we can use a time-independent Schrodinger equation to describe them. But this is not the case for many electron atoms. So new quantum numbers have to be found if we're going to have time-independent problems that we can work out the mathematics for. So things are going to get a little bit more complicated from a quantum number standpoint when we start looking at atoms with more than one electron, but less than 40. Good quantum numbers for many electron atoms can be formed for atoms with Z less than 40 by generating vector sums of the electron orbital and spin angular momenta separately. L and S, so we've got capital letters here, we'll have Z components M sub L and M sub S. So we're using a lot of the same letters that we used in the hydrogen lowercase quantum numbers, but we're giving them capital letters in this case. Only electrons in unfilled subshells contribute to these sums, because if we add up these components for unfilled subshells, they will cancel each other out and they'll add up to 0. So the quantum number capital L is going to be the summation of lowercase l. An easier way to calculate that is going to be summation of lowercase m sub l if we were using our old quantum numbers. And the quantum number capital S is going to be the summation of the m sub s's in that sublevel. So for example, we're going to do that on the next slide. You can pause if you got things you need to write down here. But we're going to do that as an example with the fluorine atom on the next slide. Let's move me up here so I'll be out of the way. So a fluorine atom has electron configuration 1s, 2, 2s2, 2p5. There's one unpaired electron. So the total spin, if you think about that unfilled sublevel, the 2p5, you have a spin up and a spin down, a spin up and a spin down, and a spin up. So the total spin is 1/2. So 2s plus 1 equals 2. We can put in a little picture to demonstrate that. Capital L, if we've put, and this is how we're normally going to fill, and we'll talk about why in a moment, we fill up m sub L equals 1 first, then 0, then minus 1. So if we add up all of the m sub L's, it's 1 plus 1 for these two, 0 plus 0 for these two, and 1 for this one. So it's 1 plus 1, 0, 0, minus 1. We get 1. If we get a negative number here, notice these lines, those are absolute value signs. So it's going to be the absolute value of that sum. And we end up with L equals 1 in that case. And J is L plus S. And so L, we just said was 1. S is 1/2. So J is 3/2. And those are our quantum numbers for the fluorine atom in its most stable state, in its ground state. This 2s plus 1 is giving us the spin multiplicity, so we would call this a doublet state. This is going to be a good spot for us to pause. We're about halfway done with our slides for the chapter, and we're getting close to our 15-minute limit with the software that I use for recording. So we're going to pick up with this topic, continue with these thoughts, and talk about not just the ground state, but the possible values for ground and excited states and how to evaluate which of those is most stable.